Hello, intermediate algebra students. Today we are switching gears to section 4.4a, and we're going to talk about graphing linear inequalities. My name is Ms. Leminski. I just wanted to introduce myself since this is the first video I'm making for you guys. Okay, so before we start graphing linear inequalities, I want to do a quick review of how we would graph an equation. Okay, so a linear equation. We've done this multiple times throughout the year. So I want you to pause the video and see if you can graph the line y equals negative 1/3 x plus 2. Hopefully you were able to identify the y-intercept as 2. That's the b value because this is in y equals mx plus b form. And as a reminder, when we graph a line, we plot that y-intercept first, so 2 on the y-axis. And then I hope that you were able to identify that the slope was negative 1/3. Which is my rise over run. So from the point at 2 on the y-axis, I go down 1, and then I run 3 to the right. To graph a line, I need 2 points. So those are my 2 points, and because it's an equation, I just draw a solid line between those 2 points. And that would be my answer if I was asked to graph that equation. Today, we're going to look at something very similar, but there's going to be a couple of extensions we have to do. Because now you can see that we are going to learn how to graph a linear inequality. So it's still a line, but now it's going to have an inequality symbol instead of an equal sign, like you see in this example. So an inequality would be either less than, greater than, less than or equal to, or greater than or equal to, in place of the equal sign. So if I go to graph this, my first step is still to plot 2 points. Just like we did in the warm-up. First, I'm going to plot the y-intercept, and then I'm going to go rise over run from there. So I always like to write down my steps as I go, but I like to do one step at a time and then implement it. So if I'm graphing y is less than or equal to x minus 1, right now I don't need to worry about the inequality. I'm just going to plot 2 points like I always would. My b, or y-intercept, is still the end number, which is negative 1. So I'd plot that point here. And now remember, if there's no number attached to the x, my m, which is my slope, be just a 1. Okay, so I could put a 1 there if I wanted to. We do like to think about slope or rise over run as a fraction. Anytime it's not a fraction, I can just put it over 1. So my rise is 1 and my run is 1. So from this point, I rise 1, run 1. Now, once you plot your 2 points, though, this is where you have to pause because it's not an equation, so I don't just draw a line through it. Instead, my second step, as soon as it's an inequality, is to decide if it's going to be a solid or dashed. I sometimes call it dotted, even though it's technically more dashed. Decide if it's solid or dashed line. Here's what you're looking for. If it's a greater than or less than symbol, then when you graph that line, it's going to be dashed or dotted because it's not included. If it's greater than or equal to, or less than or equal to, then you're going to graph a solid line, just like you would if it's an equation, because that line is part of your solution. So in this example, when I look back here for step 2, it was a less than or equal to, which means I need a solid line. Now, here's the thing that makes a linear inequality really unique. Your answer is not just the line itself, be it solid or dotted, but it's actually a region of the graph. Okay, so in this case, yes, that line is part of my answers, but so is either this half above the line or the half below. So in order to finish this problem, I need to shade a region of the graph. Oh boy, that was supposed to say of. Region of the graph. And we do that by using a test point. A couple of key things about the test point. First of all, if possible, you actually get to pick any point you want that's not actually on the line. So I could not test the point 0, -1, I could test any point up here or any point down here. I always like to test 0, 0 if it's not on the line, just because it's easier math. Okay? What I mean by testing, I'll go over here and do that real quick. So I am going to test 0, 0 because that is in fact not on the line. It means I take this inequality and I plug in 0 for my y, 0 for my x, and I simplify. Now after I simplify, I ask myself, is this true? Yes or no? Is 0 less than or equal to -1? And no, it's not. That means that if that's not true, that means 0, 0 is not a solution to the graph, which means I do not want to include it in my picture. We just said we were trying to shade a side, so if this point is not included, that means this whole top section is not included. And if the top is not included, that means the bottom part is. So I would shade the other side. So if I get no, then I am going to shade the other side of the line. Meaning the other side from where the point you tested is. If I get yes, then you're going to shade over the point. So shade the side the point is on. Okay. Now, this is my answer. That picture itself is the answer because I was asked to graph it. So when we're asked to graph a linear inequality, we do 3 steps. First, we plot the 2 points. Then we decide if it's solid or dotted based on the symbol. And then we test a point to see which side of the graph we are going to shade. Let's try another one. In this case, I'm asked to graph the inequality y is less than -3x plus 4. Again, I remember that my first step is to plot 2 points. So I find my y-intercept first. It is in mx plus b form, so my plus 4 is my y-intercept. So I've got 4, I plot a point. Then I find my slope, and in this case, it's a -3, which means I can think about it as -3 over 1, which means I rise a -3 and run 1, which means go down 3, 1, 2, 3, and run 1. So I went down 3, and I ran 1, just so we can see. Now, because it's an inequality, as soon as it's just a less than symbol, I ask myself, is it solid or dotted? And because it is not underlined, this is an example of where it's dotted. So through those 2 points, rather than drawing a solid line, I'm going to draw a dashed or dotted line. Okay? So that's a big difference. Now in Pearson, after you plot your 2 points, it automatically puts a line there. Make sure you click the dashed line after you have that graph drawn if you didn't do it beforehand. And last but not least, we need to fill or shade a region. So we use our test point. Again, I check 0, 0 is not on the line, so I can test that, which means I take y is less than -3x plus 4. I plug 0 in for my x and y, and I ask myself, is 0 less than 4? And this time I answer yes. Because 0 is less than 4, that means this is a solution. What that means is actually this would be a solution, this would be a solution, this would be a solution, this would be a solution. Anything on this side of the line is a solution. But if I had tested anything over here, I would have gotten no. Okay, so now I shade this way where all of my solutions are. Any one of those points would work in this inequality. Now again, just a little Pearson tip. After you plot your points and switch your line to dotted, there's a little paint bucket icon. You would click the paint bucket icon, and then you would click on this side of the graph, and it would shade this whole side for you. All right, now that we've done a couple of examples, I want you to pause the video and try this one on your own. I hope as you were trying this, you were able to see that your y-intercept was -3. Your slope should have been 1/2, so you rise 1, run 2. Because it was greater than or equal to, you should have had a solid line through those points. So my next step is the solid line. And then your test point, you could have used 0, 0. So when you tested it, you would have had is 0 greater than or equal to 1/2 times 0 minus 3. So is 0 greater than or equal to -3? And yes, it is. Which means that is a solution, so I should shade up over it. Okay, so that's your final answer for that one. The only other thing we're going to look at today is what happens when you're given a word problem. And we're only going to do one of these today. You will see one in your homework assignment tonight, but then we'll do another one as a warm-up tomorrow. The only difference is you're going to have to be able to write your own inequality, which is good practice of what we've been working on earlier this semester. So George is the coach of a baseball team. He has $1,000 and would like to purchase as many bats and baseballs as he can. The bats are $59 each, and the baseballs are $1 each. And he gave me $1,000. We're going to graph the inequality that represents the possible combinations of baseballs and bats he can buy. So Ms. Brodigan showed this using the Freyer model, where you would set up the question, but this is a little different because we're not actually solving for anything. We're actually just graphing it in the end. So you could try to use the Freyer model, but we're just going to process through the same way she did. And in the end, though, my question is, can I graph it? So that's the end result. Having said that, then she said, okay, the next thing is we have to figure out our variables. The two things we're talking about here are the bats and the baseballs. So I'm going to let my x represent bats and my y represent baseballs. Now, there's only one inequality here. We did systems of equations where you had to write two equations, which made it a little more tricky. So in this case, I'm just writing an inequality to represent how many baseballs and how many bats he can buy. Well, they tell me that each bat is $59. So since x is my bats, I would represent that by 59 times x. Each baseball is $1. So I would do plus 1 times y, however many baseballs I buy. Here's the only difference. Up until now, we know he has $1,000, so we would say equals 1,000. But the reality is we are not saying he needs to spend exactly $1,000. If we did, we'd put an equal sign there. Instead, we're saying that's the most he can spend, which means that the amount of money I spend, which is this side, this is the amount I spend, it's got to be less than or equal to $1,000 to be able to afford it. Okay, so we do have to be able to write inequalities given this situation. But here's the reality is once I have it, this is in standard form, I'm going to convert it into slope-intercept form just like we have been. And you will have to do that on the Pearson practice. In this case, if I want to take this and convert it, I would subtract the 59x from both sides. I get 1y, which is the same as y. So I'm just going to leave it as that. So it's negative 59x plus 1,000. Okay, so now that I have that, I could go, 1,000 is, so my y-intercept is going to be the 1,000. So I plot a point there. This one's a little tricky because it says my slope is negative 59. So technically my slope is negative 59 over 1. Well, since I'm counting by 250s, that would be like somewhere around here, but that's very generic. So that's not a great point. Another option would be to find another point on the graph. You won't have to do this on Pearson, but just as a side note, I already know the y-intercept because it's here. I could quickly find the x-intercept because I know that's when y equals 0. So I would say when is 0 equal to negative 59x plus 1,000? I would subtract 1,000 from both sides and divide by negative 59, and I got x equals 16.95. So I could, like I said, this is probably somewhere around here. I was down 59 over 1. But otherwise, on the x-axis, there's a point at 16.95. Again, on your Pearson assignment, you don't have to necessarily do that. I think it's a little cleaner. You're just looking at some options of graphs. But when I look at this, I could graph kind of through both of those. I went with a solid line because it was less than or equal to. And last but not least, I am able to test 0, 0. So if I plug in 0, 0, I could plug it into the original. It would be a little bit easier. Remember, we had 59x plus y is less than or equal to 1,000. If I plug in 0 for both of these, I just say, is 0 less than or equal to 1,000? I get yes. So this is, in fact, the part I would shade. Now notice, I stayed inside the first quadrant, so I didn't go past the y-axis or the x-axis because I need a positive number of baseballs and bats. Okay, so that's what the picture looks like. Now, having said that, what this means is that any combination of baseball and bats in that shaded area or on the line, since it's a solid line, would work. Meaning, I could buy 1 bat and 500 baseballs, right? 1 bat, 500 baseballs. I could buy 5 bats and 250 baseballs. If, however, you're asked, so if you're asked something like that and you can quickly and easily see it in the graph, just find it. 7 bats and 250 baseballs, absolutely. Sometimes they're going to ask you a question. It's a little harder to see. So if they ask me, can he buy 10 bats and 300 baseballs? Okay, then I would go over to 10 bats. Again, this is bats. 300 is somewhere between here, and the line does cut through it. But again, this was kind of a sketch. It wasn't super accurate, but somewhere between 250 and 500, it doesn't work, and some points between there it does. So if you're ever unsure, take the inequality, which I decided to take the original, 59x plus 1y, test the point and see if it works. So I took 59 times 10 plus 1 times 300 and asked myself, is that less than 1,000? 590 plus 300. So I got, is 890 less than or equal to 1,000? Yes, it is. So yes, he could buy that. Okay, so if it works, if you get yes as the answer, then yes, it works. And again, it looked like it would in the picture, but just to be 100% sure, you can always plug in those x and y variables to find out. Okay, like I said, we'll do another word problem example at the beginning of class as our warm-up tomorrow, but I wanted to make sure we got through one, and you'll get a chance to practice one in Pearson as well. Here's your note sheet for the day. It's also should be uploaded in your Schoology folder if you prefer, but this is actually everything we did. There wasn't too much, so I didn't cut anything out. And now you should go work on your 4-4A Pearson practice. Thank you.